So, in a typical realistic situation, there's typically going to be some sort of damping. Now, if we're doing things on the surface of the Earth, that means that we're moving in a fluid, i.e. air, so that adds a damping term to it. So that's why if you took a spring mass system and let it oscillate, it's not going to oscillate forever. There could be some sort of kinetic friction term, or different scenarios that are going to take energy away from the system. So we want to start looking at then damped harmonic oscillation, which means we want to add some sort of damping term. So here we're going to add some sort of drag term or some damping term to our system. Now, as we talked about back when we talked about velocity-dependent forces, typically the damping term or the drag force or the friction term is some complicated expression which depends on velocity in some complicated way. But again, for most of the scenarios, we can actually do a Taylor series expansion and then write this as a linear drag force plus a quadratic drag force, and etc. Now, if I have something which is moving, say, like in air or in a typical type of fluid or typical type of medium, typically it turns out that the drag force, or at least the damping force, is going to go something as minus b times the velocity, where b is just some sort of coefficient. So this is going to be minus b times x dot. So what we want to do then is start to add in this damping force, where b here is some constant which is greater than 0, and then see what type of effect this has on the harmonic oscillation, and see the rate at which energy is being dissipated, and etc. So, using this, we can then say that Newton's second law becomes then the mass times the acceleration. So this is the second time derivative of position, plus then our drag force, so dx dt, plus then k times x from our spring constant is then equal to 0. Now from here, if we divide through by the mass, we then get that the second derivative of the position plus some beta times dx dt, plus then omega 0 squared times x is equal to 0, where in this case we're defining beta then is equal to b divided by m. This is what's known as the damping parameter. So damping parameter. And then omega 0 squared is equal to k divided by m. This is what's known as the natural frequency. So this is the typical type of characteristic frequency that we've seen before. Now, from here, we want to do then is solve this differential equation. Now again, the way that we're going to solve it is the same way that we did before. We're going to seek a solution which goes as an exponential. And as we wrote down, what happens then is that the second derivative goes as lambda squared, the first derivative goes as lambda, and then that last one is just 1, because again, each one carries a factor of e to the lambda t, but that's going to divide out. So basically, if we then seek a solution of that form, this is going to become lambda squared plus beta times lambda plus omega 0 squared is then equal to 0, which then gives us a quadratic equation that we need to solve for lambda. So this is what, again, is known as the characteristic equation. So characteristic, also known as the auxiliary equation. So from here, remember the quadratic goes as minus b. So the solution for lambda then is minus b, which in this case is beta, plus or minus the square root of b squared, so that's beta squared, minus 4 times a, where a is simply 1, times c, which is omega 0 squared, all divided by 2 times a, which is simply 2. Now, typically, here I'm going to actually make a slight modification. And typically, you're actually going to write this with a 2 here, and let's make this a 2. Reason for that is now this is going to become a 2 here. This will become a 4. So if we factor out the 2, I get minus beta plus or minus the square root of beta squared minus omega 0 squared. Again, this is typically convention. I mean, you don't have to do this, but a lot of people do that. Again, mostly just get rid of that factor 2 to make it a little bit prettier. So good. So this means we have 2 solutions in general. So we have lambda plus and lambda minus. So let's write this as lambda plus minus. which means that our general solution is x of t then is equal to some coefficient c1 times e to the lambda plus times t plus then c2 times e to the lambda minus times t. Now, at this stage, we can't really determine what's actually going on here until we know the relative sizes of beta and omega, because here this can actually have different solutions depending on the size of beta, depending on the size of omega 0. Each one of those will actually lead to a different solution of this particular differential equation, which leads to a different physical scenario which is actually happening. So let's talk about those different physical scenarios. So let's put some requirements on these different parameters, and let's see what happens to these different solutions. So good. So okay, so remind yourselves, lambda plus or minus is equal to minus beta plus or minus the square root beta squared minus omega 0 squared. So the first possible scenario, so let's call that scenario number 1, is when what? Beta is less than omega 0. Okay. So basically what happens in this case then is that our damping parameter is less than the natural frequency of our situation or of our system. So in this case what happens then is this term is less than this term, which means we're going to rewrite lambda plus or minus as equal to minus beta plus or minus I times the square root of omega 0 squared minus beta squared. So basically what happens is if beta, the damping parameter, is less than the natural frequency, i.e. it doesn't have a lot of damping to it, what happens in this case is we can pull out that negative to make this thing positive, but then that makes this thing imaginary. Now if we go back then to our general solution, so that means that x of t is going to be equal to then c1 e to the minus beta t. And then I get a e to the, so this with the positive sign, so this becomes I times the square root of omega 0 squared minus beta squared. And then I get a plus c2 e to the minus beta t e to the minus I square root of omega 0 squared minus beta squared. So basically, what happens in this case then is what? Now, these coefficients then are complex because these guys are complex, which means this is going to be C and this is going to be C star. So ultimately what ends up happening then is this thing actually ends up going under harmonic oscillation, meaning that what? I can rewrite this as e to the minus beta t times c1 e to the I square root of omega 0 squared minus beta squared plus c2 e to the minus I square root omega 0 squared minus beta squared. So what happens is this thing is our usual harmonic oscillator, but this thing is harmonically oscillating at a different frequency. So, oops, I forgot my time's on here. Sorry about that. Should have a time here and a time here. So basically, this thing is oscillating at a new frequency of omega 1, which is equal to the square root of omega 0 squared minus beta squared. So this thing is simply undergoing harmonic oscillating, but overall this thing is being damped, and the rate at which this thing is being damped, i.e. going to 0, has to do now with this decay parameter. So this scenario is what we call underdamped. So this is an underdamped oscillator. So basically what happens is you still have harmonic oscillation, but ultimately it follows this exponential decay. Or I can write this using what we did earlier in this chapter. I can write this as some coefficient a, e to the minus bt, times then cosine of omega 1 times t minus the phase factor. Where again, omega 1 is the new frequency at which the system is actually oscillating at. So, get kind of a feel of what's going on here. Let's plot. So ultimately what this is going to be doing is it's going to have an exponential decay superimposed on top of harmonic oscillation. So if I draw this thing, so let's draw position as a function of time. So first I'm getting the exponential decay, so this thing is doing this. So this is our e to the minus beta t. We also have harmonic oscillation. So let's say, for funsies, this thing starts off as a cosine curve. So this is going to be doing what, harmonic oscillation. So doing something like this, and etc. So ultimately, if I superimpose those two things on top of each other, and we look at the position as a function of time, and this is my position, so this thing is going to undergo harmonic oscillation, but under every oscillation, this thing is actually going to damp exponentially. So this is going to follow our exponential curve, so e to the minus beta t, and this thing is oscillating with a frequency of omega 1. Now, depending on the size of beta will basically determine how many oscillations I get before this thing goes to 0. But again, typically this thing won't actually go to 0 until infinity. At least time goes to infinity, which means technically we're going to get an infinite number of oscillations. Now, the amplitude between successive oscillations, so if I was looking at this point versus this point, we know time-wise the difference between these is simply the period. So here, this thing is at an amplitude of e to the minus beta times some time. And then this one here is at a e to the minus beta times that time plus the period. Right? So the period here I'm defining as tau. So if I take the ratio between the two of these, I get a e to the minus b time divided by a e to the minus beta times t plus the period, which is the same thing as e to the beta times the period. So this quantity here is what's known as the decrement. So that tells me how much my amplitude then decreases, or at least how much the amplitude has decreased going from successive peaks. And again, the period here is determined by that new angular frequency, omega 1. Good. So this is what's called, again, underdamped. So underdamped is you still have harmonic oscillations, but overall the overall motion of it will be exponentially damped due to the fact that there is a damping term. But again, this damping term is less than the normal frequency or the natural frequency of our system. So what happens to the energy? Well, in this case, we know that the total energy is equal to the kinetic energy plus the potential energy, which is then equal to 1/2 the mass times that position as a function of time, the derivative of that squared, plus then 1/2 of the spring constant times the position squared. So basically to do this, what we'd have to do is take that expression that we just wrote down, take derivatives of that, and then plug that back in here. It's a little long and drawn out, so I'm not going to bother doing all the steps here. I'll let you kind of fill those in, but basically you'll have to use a couple different trig identities. So the first trig identity you're going to need is that cosine squared of x minus sine squared of x is equal to cosine of 2x. And that's 2 cosine of x sine of x is equal to sine of 2x. So using those in the definition of beta and omega 1, what we finally get then is that the total energy of the system is equal to the mass times the amplitude squared divided by 2 times e to the minus twice the damping parameter times the time, all times then beta squared times cosine of 2 omega 1t minus delta plus beta times the square root of omega 0 squared minus beta squared times sine of the same term here plus omega 0 squared. So this is then the total energy of the oscillator. So from here, we can also ask the question, how fast is the energy dissipating? So what is the dissipation rate then of the total energy? So let's do that here. Keep these guys up for now. So if we do that, we find then is that the rate of change of the energy then is equal to, so it's a little bit longer expression, so the mass times the amplitude squared divided by 2, e to the minus 2 times beta times t times 2 times beta times omega 0 squared minus 4 times beta squared times cosine of, let me call that alpha, plus, where am I? Minus, sorry, 4 times beta squared times the square root of omega 0 squared minus beta squared times sine of alpha minus twice of beta times omega 0 squared, where alpha is defined as twice of omega 1t minus delta. So this is the rate at which energy is then being dissipated from the system. Now, first thing to note here is that, notice that both the energy and the rate at which the energy is changing are both actually sinusoidal as well. So this, again, has harmonic oscillation, it's sinusoidal. This one also has harmonic oscillation to it. But they all are both damped exponentially. So what will happen is what? As the time is going on, the energy will oscillate, but it will be in a damped fashion. So it's going to have an overall exponential decay to it, which goes as minus 2 beta. And then the energy also sinusoidally changes, but again, it's exponentially damped. So eventually it's going to go to 0. So eventually all of the energy, which is in the harmonic oscillator, initially will be given off as either thermal energy, given into the medium itself. So the medium will actually heat up as this thing is actually decaying. So all the energy from harmonic oscillator will turn into thermal energy inside of the medium. So just going to put this in a little bit of context. Let's plot this for some different variables, different values, and see what this should actually look like. So here, if I plot the energy versus time, in this case, what will happen is, again, this thing is going to follow the exponential decay. So this goes e to the minus 2 beta times time. But again, there's oscillatory terms to it, so this thing is actually going to do something like this. Okay. So this will be then the total energy as a function of time. The rate at which the energy is changing then as a function of time, in this case, ends up doing something like this. So again, we have the exponential decay here, e to the minus 2 beta t. But again, there is oscillatory terms to this guy. So again, this is what we call underdamped. So again, an underdamped situation, again, the energy is given off as thermal energy to the medium, causing the medium to actually heat up. But there is sinusoidal oscillation with the overall exponential decay. Scenario number 2, let's look at scenario number 2. Scenario number 2 is when beta is equal to omega 0. So in this case, what happens then is what? Lambda plus and minus is going to become minus beta plus or minus the square root of beta squared minus omega 0 squared, which is simply equal to minus beta. So what that means then is that both of these two terms are exactly the same. So lambda plus and minus become the same. In this case, what will happen then is our general solution is going to become x of t is equal to some coefficient c1 plus some coefficient c2 times time times e to the minus beta t. So basically what will happen in this case then is, again, we have simply exponential decay, where this thing is simply going to exponentially decay to 0. So in this case, if I plotted the position as a function of time, this thing is simply just going to do that. This is going to be our e to the minus beta times time. So here, for this scenario, which is called critically damped, we'll talk about why this is critically damped in a little bit. What happens then is that the overall motion is simply exponentially decaying. So typically what ends up happening is C2 here is typically equal to 0, which means we only have C1, which gives us the exponential decay. Otherwise, if this one existed, it would actually end up linearly increasing at first, but then exponentially decay from there. But the way in this thing decays is actually the fastest that it's going to decay at. Now, here the scenario is still the same. What happens then is as it's actually exponentially decaying, all of that energy again is going to be dissipated into the medium, in which case the medium again is going to heat up. So give you kind of an example. Typically when you're driving in your car and you go over a bump, you might bounce maybe once or twice before you go on. Again, especially if you have older shocks. In that case, that's typically going to be an underdamped situation. Here, critically damped would be you go over a bump and it basically just levels right out. Right? There is no harmonic oscillation. It just goes straight into exponential decay. Good. So, finally, scenario number 3. Scenario number 3 is the last case, which is when beta is greater than omega 0. So here for scenario 3, we have beta that is greater than omega 0, which means that lambda plus or minus, again, is going to be equal to minus beta plus or minus the square root beta squared minus omega 0 squared, which means both of these two terms are real. So as long as these two terms are real, that means that we have no more, again, harmonic oscillation, so that our general solution, again, goes what we originally wrote down. So this is going to be like C1 e to the minus beta times time, plus then the square root of beta squared minus omega 0 squared times time, plus then C2 e to the minus beta times time, minus the square root of beta squared minus omega 0 squared times time. Now, typically what's going to happen is this term is going to go to 0 much more rapidly than it did in the critical case, but this term is actually going to go to 0 much more slowly than it does in the critical case. Because here you get this extra term, which is causing it to go to 0 faster. Here you get that plus sign, which is then giving you an exponential term, which is trying to grow, while the other one is trying to decay. But ultimately, this term here will be smaller than this term by itself because of that negative sign, which basically means that ultimately the exponential term is going to dominate. So it is going to go to 0 at some stage. Now again, typically what happens in most physical situations, C2 will end up being 0. So you're left with this C1 term, which again means that it's going to go to 0, but it's going to go to 0 slower than what it does in the critical case. So what ends up happening here is if I plotted x as a function of time, in this case it's still going to exponentially go to 0, but now it's going to go to exponentially 0 slower than what it did in the other case. Right? So this is what we call overdamped. So in an overdamped situation, you have that the damping parameter is greater than the natural frequency, causing it to actually decay slower, as opposed to this situation, which is then the critically damped. And here, the other one, which is the harmonic oscillation, this one has the same damping rate, but again, this one is actually harmonically oscillating. So these are the 3 scenarios superimposed on top of each other. So again, this is the underdamped. This is the critically damped, and then the blue is the overdamped. So the weird thing that's happening here is that in most scenarios, what's actually happening is that there's so much damping that the damping is actually interfering with how fast that it's actually going to damp out, which means that the damping is actually killing and actually destroying some of that damping, which is causing it to take longer to actually dampen out. So let's define what's called the decay parameter and talk about why critically damped is called critically damped. So let's define what's called the decay parameter, which we're going to call alpha, which is then equal to basically the value of the argument of the exponential. So for So basically for underdamped, this is simply equal to beta. Remember that beta was greater than omega 0. For critically damped, this was also equal to beta. So you have beta was equal to omega 0. And then for the overdamped, you have minus beta plus or minus the square root. Sorry, minus in this case. Beta squared minus then omega 0 squared. This was when beta was greater than omega 0. So basically, let's do a plot of this. So let's plot alpha divided by the natural frequency here, and then let's do beta divided by the natural frequency here. So basically what's happening again, when beta is less than omega 0, this thing is then growing linearly with beta until I get 2, 1, where this thing now reaches its maximum beta value. And then after that, this thing is then going to decrease, and it decreases something like this. So basically, this occurs then at what? 1. So what this says then is that the greatest that the damping can be is when what? Alpha is equal to beta, which is when beta is equal to omega 0 because we have it equal to 1. So this is why it's called critically damped. It's called critically damped because this thing then has the greatest amount of damping at this stage. Now, overdamping has some interesting phase space diagrams to it. So we kind of talked about the phase space diagram of a damped system. In that case, I was actually talking about the underdamped. In that case, where I said for an underdamped. Here, if we look at the phase space, where again I do dx dt, x on this axis, again this thing actually is going to end up doing something like a spiral. And again, we know this has to make circles because it is harmonically oscillating. But if I look at an overdamped situation, actually weird things can actually end up happening. You get interesting diagrams in this case. So let's look at what happens here. So if I look at dx dt on this axis, look at x on this axis. So basically, this line here, this dotted line, corresponds to when x dot is equal to minus beta plus omega 2. Find what that is in a second, times x, where omega 2 is equal to the square root of beta squared minus omega 0 squared. So basically, omega 2 is equal to what? Minus I times omega 1. So good. So basically, what happens is for different sets of parameters, what will happen is this thing will start at some position, but then it'll quickly then decay to this asymptotic line, and then it'll go to 0 along this asymptotic line. So for example, if we start off with an initial position and initial velocity, which are both greater than 0, so if I start off with, say, x initial and x dot initial, both greater than 0, so I'm starting off at a point here. Basically what will happen is this thing is going to quickly die down to this line and then follow this in along this asymptotic line. Now if I start off with one where, let's use a different color, what haven't I used yet? I guess orange is fine. We're going to use that x0 is greater than 0, but the derivative is less than 0, so this thing is going to start off, say, something here. Again, it's going to basically quickly decay to this asymptotic and then ride along this particular asymptotic. This thing can easily change signs, as we're basically seeing here. So what's happening here is the velocity starts off positive and then goes to negative, and then it exponentially decays along this particular line. Here, the velocity stays with the same sign. So we can actually get some very interesting types of behavior from these different scenarios based off of the initial conditions for this overdamped situation. So again, these are the three possible different damping situations that we can have. Again, here we just have some sort of damping term which is proportional to the velocity, not the velocity squared, but just the velocity. So again, what's happening as this thing is harmonically oscillating, it's losing its energy to whatever medium that it happens to be in. So all that energy is going to go into thermal energy, causing the system to actually heat up. But for the three different scenarios, we have different requirements on then that damping parameter, which then lead to different decay parameters, which then lead to different types of harmonic oscillations.